So it's time to start. So let me introduce Chen. Chen is a discrete geometer that has entered pretty recently in minimal surface theory. And he comes from Göttingen University, where he had a postdoc position. His advisor was Gunther Ziegler, and the title of the thesis is the triplet periodic minimal surfaces in genus 3. And we'd like to also mention that she has worked with Weber and Treset, which are very good friends of us, and on Gruen techniques with Treset, and on triplet periodic new examples of genus 3 triplet periodic minimal surfaces with Weber. Okay, so, and he's going to also to give us 3 talks. No? This is just the first one, but the second will be about Gruen techniques with Treset, I guess. And the third one is I'm looking forward to see it because it's about the material sciences and applications of minimal surfaces. So thank you.
Thank you. So thank you for having me here. First, something about me. So as already mentioned, I was trained as a discrete geometer. So before 2017, my focus of research was polytopes, sphere packings, hyperbolic groups, and so on. And around 2017, I moved to the topic of minimal surface because of my scientist wife. And at the beginning, it was a after-work hobby, just playing around. And then it became more serious, and I get fundings from the Deutsche DFG, and this becomes my focus. And I'm currently in academic refugee because I was supposed to be in Shanghai, which is not a trivial task now. And the preview of my 3 talks during my stay here. This is the first one about triplet periodic minimal surfaces, and mostly about those of genus 3. And then the next one, I will talk about moving saddle towers into minimal surfaces. So not necessarily triplet periodic. So during the time, I expanded my interest. And the last talk is about interdisciplinary aspects. And actually all my works, though pure mathematical, actually are inspired or motivated by other sciences. And voila. So what is a triplet periodic minimal surface? So it is first a minimal surface, and then it is periodic. So it has the symmetry of crystals. So that's very fantastic. We have one beautiful thing, minimal surface, as the bubble films. The other beautiful thing, the crystals. So those 2 things put together, you get a triplet periodic minimal surface. And here, for those who recognize this, this is one of the most beautiful triplet periodic minimal surface we have. And my goal is to classify all triplet periodic minimal surfaces of genus 3. And why genus 3? Because that's the minimum genus that is possible for this kind of minimal surface. And how far are we from this goal? We are still very, very far. But today's focus is that we can still make some progress, even though I think the complete classification, we still need 10 years or something. So history before 2000, the year 2000. So the history of minimal surface goes back to Lagrange, and but the first examples of triplet periodic minimal surface goes back to Schwarz. And at the time, he actually gave the first explicit solution to Plato's problem. And his Plato's problem asks, if you are given a frame, what would be a minimal surface that is bounded by this frame? So for Schwarz, he had 6 degree, 6 degree, and 60 degree, and 90 degree, 90 degree, this frame. And he gave explicit solution to this frame. And then, because we have these straight lines, you can rotate your surface around these straight lines and expand your surface. And it turns out that it covers all your space. It runs all over the space, and it becomes triply periodic. And if you quotient out the translation symmetries, these surfaces, seen as surfaces in flat tori, flat three-dimensional tori, they are all of genus 3. So all his examples are of genus 3. And they all reduces to this kind of structure. So if you quotient out the rotations and the reflections, they all reduce to small pieces, and these small pieces are simply connected. And because of this, so in his language, it is called Flächenstück. And because of this, all these can be parameterized, I mean, vice parameterized on the upper half plane, because you can map the upper half plane to a minimum polygon, and then extend your surface by reflections and rotations and so on. And he actually knew many 1 parameter and 2 parameter deformation families, but he wrote it in the appendix. So later people didn't notice that. And here are some of the examples. I can give you an idea of the first one, Schwarz-P. And this would be a minimal hexagon. That consists of Schwarz-P. And you see all the faces that intersect the minimal surface are reflection planes, and you can scan this. So, and we have other Schwarz-Ditch, Schwarz-CLP cross-layered planes, and so on. So these names are strange. I will talk about it later. Why is it?
Maybe because the door is closed. You sure? You need to open the door.
Good. Yeah. Anyway, as long as working is so. The next examples must wait for almost 100 years until Alan Chen, who was a NASA scientist, and he found a lot of. I think he was bored during his work, and he began to play with models, and he found a lot of examples. Most of them are of higher genus, except one, the gyroid that I showed you. And most of them contain planar curvature lines, reflection planes, and straight lines, except gyroid. And most of them are proved later by Cartier by conjugate Plato method, except gyroid. And gyroid was proved much later, I think in 1990s, by Bosse Baumann and Wolgemuth. And what is, yeah, this gyroid? The thing is, it has no straight line in it. It has no natural reflection plane, and it is not, later. Yeah. Around the same time, we have Bill Meeks, who constructed a large family of minimal surfaces. Okay, so all of so he proved that first, the genus of triply minimal surface is at least 3. And then those of genus 3, I abbreviated as TPMS G3s, they can be parameterized on branched double cover of the sphere with 8 branch points. And these 8 branch points corresponds to 8 flat points. Flat points means those points with Gaussian curvature 0. And all these points can be up to us. So I draw, this would be a parallelotope that represents a 3-dimensional torus. And 2 division points are either 0 and the center of the edges. Center of the edges, that means we only take these 3, and center of the faces. The other one is somewhere here, and the center of the body, center of the cell. That's the 8 2-division points. So you can move, by a translation, you can move the flat points to these 8 points. So that's really nice. And Bill also considered a family of triply minimal surfaces of genus 3 with orientation reversing translational symmetry. And he proved that these surfaces form a 5-dimensional family, continuous family. And this form a very nice manifold. And for these surfaces, the 8 branch values on the sphere form 4 antipodal pairs. So, and the mixed family included almost all examples known at the time, except, again, gyroid. And another exception is Schwarz edge surface. And Bill actually gave some concrete examples, but Matthias Weber told me that actually all his examples was known to Schwarz. But no offense, but this is not your fault. Actually, if you ask me today to draw a picture of, to draw an example from mixed family, I can only give one that is already known to Schwarz. For all the others, we understand it is in mixed family, but we have difficulty to visualize it. So the understanding is still limited. And it is still the only explicitly known 5-parameter manifold. So why the number 5 is important? Because 5 is the number of, is the dimension of deformation of 3-dimensional tori. So if we have a 5-parameter family, that means we have local rigidity. That's nice. Okay, then contributions from scientists. Why natural scientists are interested? Because triply pyramidal surface or structures similar to triply pyramidal surfaces, they occur everywhere in nature. Like this butterfly. The color of this butterfly is fantastic because if you look from different angles, you see different colors. And this is because there is a triply pyramidal surface structure here. And also they observe the structure in the in something about the cell. I don't know what it is because I'm not a biologist. And they also observed something in the neutron star. So everywhere in nature. So they became very interested in the topic and they digested Nick's work and digested Chen's work. And they eventually made a contribution. So this is Sven Ding. I think he's one of the member of committee in the Nobel Chemistry Prize. So what do they find? So all these, yes, I need to explain the notations. So the naming system is not by mathematicians, it's by crystallographers. So we have P, E, and G, and so on. These are names for the original examples, Schwarz examples, Chen examples. And then there is this T, and T means tetragonal. So all these have unit cell being a cube. And here we have unit cell being a prism over a square. And here we have R means rhombohedral. So its fundamental cell is one such that it's a parallelogram spanned by 3 vectors whose the angle between them are all alpha, have the same angle between them. And we also have the O orthorhombic, not in this picture, but we will orthorhombic. It would be a prism over a rectangle. And then monoclinic. It would be a prism over a parallelogram. So this is alpha, and alpha is not 90 degrees. So this is some remark about the notations. So all these black lines, they were known to Schwarz. So TD would be a tetragonal deformation of the Schwarz B surface. TP would be tetragonal of deformation of Schwarz P surface, and so on. And I'll tell you how Schwarz TP works. T can be seen as this. It is a catenoid, but not with circles, with squares. So you first get a catenoid bounded by two squares, then you rotate around the straight edges. This is one way to get P surface. And TP is just you stretch or compress the distance. You change the distance between the two squares. And what is this RPT? So it's a rhombohedral deformation family that contains P and D. So simply that. And it is spanned by two triangles that is opposite to each other. And you take a catenoid between them, and then again rotate around the straight edges. Then this family is obtained by moving, changing the distance between the two triangles. But note that when we do these, you cannot change the distance too far away, because then you don't have a minimal surface anymore. Yeah, so that is a remark about these points. Anyway, now these four guys, they discovered rhombohedral and tetragonal deformation of the G, the gyroid. They discovered it numerically, meaning that they close the parallels only numerically. They don't have proof, they have a very nice picture. And okay, so this is the state of the art. And yeah. Yeah. How do I go back? Yeah.
What is the name of this one? Two?
Shelf tower or one and the conjugate of shelf tower. So they have the limit, and here it's actually there is one side is the helicoid limit, and the other side is catenoid limit.
And the red things are bifurcations.
The blue things are bifurcations, and these are bifurcations, but they didn't know at the time. So yes, I will talk about it. So this is the
this picture complete in the sense that
no,
there is no up to now.
No, we know a lot of orthorhombic deformations, but that's difficult to draw. So these are one-dimensional families. So they are subfamilies of known families. So the state of art, we have black lines representing the examples known by Schwarz. We have a standalone example by Chen, and we have mixed family that contains almost all of them except two exceptions. And we have physicists who know numerically an example that pass through the gyroid and also intersect the mixed family. So this intersection is interesting because it means we have singularity in the modular space of triplet pyramidal surface of genus 3. Okay, so a comment on the strategy up to now. So it's like we want to find all triplet pyramidal surface of genus 3, and now it's like playing a jigsaw puzzle. And what's the strategy of jigsaw puzzle? You played a special piece. For example, I find the head of the camera. If I did that, I can easily expand from these special pieces. So what are the special pieces now? The Schwarz examples, and then we expanded from this and find a lot of examples. And shows the gyroid is one. And also we try to expand, but not yet succeeded. Okay, so this is one strategy. And before going forward to talk about new examples, here's the bifurcations. Because if I want to continue my expansion, I need to find a way to find, so where do I start my expansion? And here, sorry, this is, there is a phrase that is covered. So a good tool for this purpose is Morse index. So it was recently proved that if you have an odd jump in the Morse index, then you have a bifurcation, meaning that when you deform your three-dimensional tori, usually the minimal surface has a unique way to deform. But at the bifurcation point, the minimal surface will have different ways to deform. And that's a strange thing. And if you have odd jump, they prove that there must be a bifurcation. So you see all these blue points, 2 to 1, it's an odd jump. And 2 to 1, a lot of odd jumps. And on the short segment of H, you have a 1 to 3. So that is a change of Morse index, but this is an even jump. So they were not sure that there is a bifurcation here. And yeah, another comment on the strategy. So what is a better way to play the jigsaw puzzle? You play the angle, the corners first, then the edges, and then expand from there because the corners are easier. So do we have something similar? I think this node opening technique is actually doing this. So this is a powerful construction near the boundary of Teichmüller space. So why do I put boundary in quotation mark? Because there are many much better definitions for Teichmüller boundaries, and this is just an oversimplified notion of boundary. And Tezet was not so interested in minimal triplet minimal surface of genus 3. He was interested more about an example that has no symmetry. So has a high genus. That was the point of that paper. And the vice class data in his work was defined on Riemann surfaces that is near noded limit. So what are noded limit? So the picture on the left is a noded surface. So it has a singular point. It can be seen as you take two Riemann surfaces and take two punctures on them and identify the punctures. And then we use a technique to open the singular point into small necks. And this is called node opening. Then for this thing to be able to be mapped to a minimal surface, you need the conformal type of the Riemann surface to be balanced. And the meaning of balance depends on the situation. And but we can see here what would be related to the conformal type. First, the conformal type of each component Riemann surface. Then the position of each punctures to be identified as singular points. Then when you open the nodes, there is a den twist, a dimension of den twist that also concerns the conformal type. Then to get a triplet minimal surface, what you need is two torus, then you need to loop them at, so you need to identify two singular points and open them as nodes. So let's try. We take a square torus. And so this is expanded by 1 and I. And I glue the 0 on the left torus to the 1 plus I over 2 to the right torus. And I glue the 0 to the I plus 1. That would give us the conformal type of a Schwarz-P surface on the. So there was a video here, but I cannot show it now because it's PDF now. So to get the right picture, I take tau equals so this is 60° first. And I identify 1 plus tau to 2 and 1 plus tau to 3, sorry, to 3. This would give me the Römer-Heyting P and V surface. And I can actually do another choice. If I know one is 1 0 to 1 plus tau over 3, another 0 to 1 plus tau over 3 minus. This would give me Schwarz H surface. So this is how the node opening would give me triply parametric surfaces. Okay, now I can talk about the recent discoveries. First, I was playing numerical games, and during this, I luckily find the clue of a new triply parametric surface. So the upper family is known to Schwarz. So it is a deformation of Schwarz B surface up to the helicoid limit. The lower family is one that I discovered just numerically. And I was surprised because this is the same deformation of the three-dimensional torus. You simply compress the cube. And you have two different families, deformation families. The other go into catenoid. And that's the point that I began to learn about constructions of minimal surface and so on. And I wrote a proof of the new family. And I sent it to Matthias Weber, and he was surprised because he said, well, in his word, he tried a lot. And every time he finds a new example, it turns out to be an old example. But this is indeed a new example. And now this is a precise picture. The previous picture is numerical. This is a precise picture. So we have the two families. They always share the same three-dimensional terrain, but they merge into one. If you continue further, they become exactly the same. So this is the, and we know we can completely describe, we can precisely describe where this point is. So this is the first explicitly described bifurcation. And a brief remark about the construction. Actually, the construction is easy because in this example, we still have straight lines and reflection planes. So we simply take a minimum hexagon that has free boundary condition on the lateral faces of this cube, of this box. It is not necessarily a cube. And with fixed boundary condition on the segment that bisect the upper and the bottom faces. So, and there is a solution that is Schwarz, the classical Schwarz D surface. And our surface turns out to be another solution. So we prove the existence of another solution to this boundary problem. And this work actually revealed a explicit bifurcation branch from that point, which the explicit branch was not known before. And actually, we also find a bifurcation branch from this point, but using similar techniques. But it is boring because the new branch is still in Nick's family. So everything in Nick's family, I consider it boring. And yeah.
So the H is hexagonal surface?
The T?
H.
H is the hexagonal surface. It's two
Hexagonal, yeah.
Yeah, it's two triangles.
That's where it's hexagonal.
Yeah.
H surface. Where it's H.
Yes.
So it looks like from here everything's connected. The spaces have all those examples of the count.
Now, yes. So if we confirm the diagram, yes.
Yeah, you have the G.
Yeah, but these are up to now. It's only numerically known.
Oh, right. You may have more examples.
But 10 seconds later, it will be known. Anyway, so then we use very similar technique and construct a new OH. So now you know O means orthorhombic, and H means it is a family that contains Schwarz H family. And what is the motivation of this? So as I say, you can open the nodes by from the square. So you take one node on the 0 of the square and then take another node in the center of the square. And then you can take a triangular lattice and take another node in the center of the triangle. So here you have two choices, A or B, but they are the same. For triplet pyramidal surface of genus 3, they are the same. So I take A. So the problem is when you deform your rhombus from the square to the triangle one, there must be a point where the two choices A and B merge. And where is this point? Now we know it's something about 70 degrees. And if you want the exact formulation of this value, I can give you, but this is covered now. So this is our motivation. We want to find the bifurcation point where the two possibilities merge into one. And the construction, same game. We take a minimum octagon with free boundary conditions on the lateral faces and fixed boundary condition on the two segments. And one solution would be Schwarz p-surface, a deformation of Schwarz p-surface. And the other solution turns out to exist. And this is deformation of Schwarz h-surface. And very interesting. So from this work, we discovered that there is indeed a bifurcation branch from that bifurcation point. That's an even jump. And so this leads to the question. So does their result expand to even jump in more singles? So if not, in which cases does it expand? And as you see, the construction technique, so I'm very lucky to have found these new examples, but the construction technique was not new. I still use the straight lines and the reflection planes. So Matthias Weber gave me this challenge. So if we want to really understand the modular space of minimal surfaces of genus 3, we need to give a rigorous construction of these deformation families of the gyroid. So I finished it. And the technique is this. I put vice-class data on branched tori. And these deformation of the gyroid turns out to be in the associated family of twisted catenoid. I will give you a picture later. So the technique actually, it's fantastic that it only depends on the screw symmetry, so which gyroid it has. So it has all the four and all the three screw symmetries. And it might work to construct all triple pyramidal surfaces of genus 3 with a screw symmetry. This actually, all the examples that we explicitly know now have screw symmetry. So that's very strange. So if we cannot completely classify all of them, maybe we can first classify all the screw symmetry examples. So what are twisted catenoids? So I said that the Schwarz p-surfaces can be generated like this. So my first idea was, my first idea was, what if I twist the two squares? And you will generally see this picture. But this picture is not enough yet. So there is a very subtle detail that you cannot see with human eyes. I will draw a exaggerate the picture. They are not actually squares. They are this. So the edges are not straight. They are very, very slightly curved, and they are centrally symmetric. And then to describe these so-called twisted catenoids, you need a twist angle, and you need the distance between the squares. And this actually corresponds to the shape of your torus. And here are the pictures. So in these pictures, the horizontal axis can be seen as the twist angle. And the vertical axis can be seen as the distance between the squares. And I find these solutions. So first, there are some classical solutions. On this line is classical rhombohedral P surface. On this line is H surface. On this line is tetragonal D. On this line is tetragonal T. These are classical examples. And these circles, they are CLP, and this is not embedded but immersed minimal surface. It's called HCLP. But so apart from these classical examples, I also have two new solutions. One actually gives the tetragonal gyroid, and the gyroid is there. And the other actually gives the rhombohedral gyroid. And you have ligninoid and gyroid as special cases. So, yeah, this is about, and in this work, so we finally confirmed that there are bifurcation branches, and the physicists are right all the way, like 30 years ago. So we finally proved the pictures that they drew very precisely 30 years ago. Okay. These are expanding from known pieces. So that's just one strategy to play the jigsaw puzzle. And here are another way to expand from the boundaries. And first, what are the possible boundaries? We have Riemann limit, the limit by Riemann surfaces, and doubly periodic limits. And I conjecture that they are boring, means that all these constructions can only lead to the boundaries of mixed manifold. And then we have helicoid limit. It's done. The construction is done. And mathematically, it's boring, means it's on the boundary of mixed family, but physically, it's interesting. I will show you. And the simply periodic Scherf limit, so gluing Scherf towers, it's done and interesting. Interesting means that we there are examples that we don't understand yet. We can describe the balance condition, but it's not enough. We still have some examples that we don't know. And the catenoid limit, it's done, and extremely interesting means that we do not know most of the examples, despite the fact that we can describe the balance condition. And conjecture. These are all the possibilities.
All the limits of what? Complete list of all.
Sorry?
Okay, so conjecture. The above is a complete list of what?
The above possible the above boundary pieces is a complete list. So if you have a diverging list of triplypyramidal surface of Gen3.
Oh, divergent.
Yeah, they all go to all one of these.
Oh, genus 3.
Yeah, of genus 3.
Oh, genus 3. Oh.
Yeah. And
I don't know that.
well, I strongly believe that.
Okay, so right. So
because
there is no symmetry.
Yeah, because they all
No,
go to
no translational symmetry.
no. Because
So,
yeah.
Okay.
Another question?
You mean polyperiodic Katcher mix Rosenberg is a complete three-dimensional family what you are meant there, or
Yeah.
so this is a three-dimensional space of possible limits in the
Should be 4. Should be 4. So that family is 3.
Rosenberg is a three-dimensional
Yes.
space.
Yes, but then there is another dimension that comes from the gluing twist.
From the what?
The gluing twist. When you glue to planar ends, you can.
Yes, because the Katcher mix Rosenberg, they do have always parallel elements.
Yeah. Yeah.
And then you lose this.
Yeah. So they have balance within themselves, and but when you glue two planar ends, you can twist them like this. So it is not necessary that they glue in a unique way. And this is another dimension. And it's like For example, if glue 4 wing saddle towers, the 4 wing saddle tower is a one-dimensional family. Yes, and when you glue 2 sharp ends, you can move one with respect to the other, and this does not. This balance does not reflect in the balance of a single saddle tower. So this is a very subtle interaction between them. So all these, if I describe their gluing, I need 4 parameters. That's for sure. And then there is the family, so the growing parameter, that's the 5th parameter. That gives the triple dimensional surface of genus 3. Anyway, so yeah.
Can't just prove this by
No, Dave.
but just the limits all have total curvature, like maybe less than 4 pi or something. I don't know what it means. That's very cool. I mean, right. So genus 3, your total curvature, oh, it's 8 pi.
Yeah.
8 pi. So you don't get 8 pi, so you have to get a multiple. If it's you assume it orientable, right? If you assume that.
Yeah.
Then you're going to get only limits that have total curvature.
Yeah, and the Gaussian curvature must converge somehow.
And then you have a classification of those examples.
Yeah.
So why don't you know the conjecture?
It's just not written down actually.
Okay. Okay, so you think it's provable, right?
I think this is an easy task.
It's what?
It should be easy.
It should be easy by total curvature. Because you can classify all examples of finite total curvature 8 pi.
Yeah.
Quotient space, which may be all part of it.
Yeah.
And those are, I'm guessing, are the only possible.
Well, my idea is their limit must be noted, and there is then you can. So if you decompose your Riemann surface by shrinking some curve into a singular point, you decompose your Riemann surface into smaller Riemann surface. Smaller means simpler topology and less punctures and so on. And all those have been classified. Therefore, I have this list.
But let me just ask you, is that it's classified, right? 8 pi or less?
I haven't seen this video, but
But 8 pi or less is classified.
I think it's
Very high.
Yeah.
So
the only possible free manifold
Yes.
that you end up with
a flat
by
number.
taking limits, flat ones.
Yeah.
The classification, I think, is that.
Yeah.
Yeah. So all simpler examples have been classified. And if you take the limits, they must be decomposed into simpler examples. And so I believe this is done, but I just didn't write it down. Okay. So, but after this conjecture, I still need to write down the construction and say it's boring. Oh, well, this is a boring task.
Well, there is something that I don't know.
Which is much fun.
If you go to a limit which is a doubly periodic minimal surface, and the ends are not parallel, the top and bottom families, then that modular space is not graphical.
You mean those are here and here?
These are not. If those two families are not parallel,
If they're not parallel, the total curvature. No.
And
you have okay. So the genus is 0, you classify.
for genus 0,
And with two fundamental domains, I think it has to be genus 0.
okay, that is done.
I don't know.
So could you go to a limit which has genus 1?
You can make genus 1 example, I think, by taking a different fundamental region.
Yeah, I only need genus 0. I only
genus 0 is classified.
Yeah, that's
in
enough.
all cases.
Yeah, that's enough. Because if I want, I have 2 parallel and like this, I need 2 copies of such surfaces, and these two wings glue to the another example. These 2 wings glue to another example. So I need 4 spheres, 2 spheres, genus 0, and each have 4 punctures. And this glue to this glue to this. And this is genus 3.
Yeah, right, doubly periodic and non-parallel ends, I think, means the genus is 0. Right? If you have total river.
And then these will take
So yeah, this conjecture, it's just not written down. But anyway, for example, for the helicoid limit, I said it's boring, but physically it is interesting. So I hope this works. So this is a video I made. So this is vortices in two-dimensional fluid that interact with each other. But I actually didn't fix all of them. I just fixed one of them. Because if I don't fix any of them, they will drift away as a rigid body upwards. But I fixed one of them, then you can see that all the others are fixed automatically. So these are called crystal, vortex crystal in fluid dynamics. And it has been studied for 200 years. And
So you're saying it's stable configuration.
yeah, it's equilibrium configuration. And where is the other one? This is a minimal surface. And I obtained by gluing helicoids. And where do I put the helicoids? I just put them at the vortices that I just see. Turns out gluing helicoids and the interaction between vortices, these two things are exactly the same. So for example, Matthias Weber and Martin Herzeg, they once glued helicoids, assuming that all the helicoids are alive. And this solution, they find it by Hermite polynomial. And this solution was actually known in 1830 something. So then let's check. We have a lot of solutions by fluid dynamicists. And all of them give us a minimal surface. And for example, this is one already known to fluid dynamists and give us a new minimal surface. And then there are minimal surfaces that we do not know the fluid dynamic correspondence. But I luckily found this photo from a Japanese engineer. And this shows, I say, wow, this is a rhombohedral P surface near the helicoid limit. So this is how, so it's mathematically boring, but physically it is very interesting. Then saddle tower is a more interesting thing. So saddle tower, it can be seen as the singularizing intersecting planes. Okay, and there has been many examples. And the main message is this: if you have a graph that is whose length functional is locally minimized, then you can take the graph times R and singularize it into a minimal surface. And the balance condition, previously known balance condition, is that the unit vector along the wings should sum up to 0. That's the only one. But the problem is all these examples, they have a horizontal reflection plane. The question is, can we get rid of this horizontal reflection plane? And this is recently done. So first, I have my gyroid deformations. They are not horizontal, they are not, there is no horizontal symmetry plane. So this is the motivation. And you see here, we must consider the twist between of nose, the shift between the saddle towers. And now here, so after this work, I have these new examples of triply pyramidal surfaces of genus 3. So how to read these? Each node is a saddle tower, and each edge is a wing. So for example, this in the middle is a 6-wing saddle tower with wings extending along the edges. And the edges have directions. And then the labels on the edges is the phase difference between saddle towers. So for example, if you go from T1, this edge to this edge, means that the saddle tower in the center is higher than the saddle tower on the corner by A, where A is a number between 0 and 2 pi. So because that 2 pi is the period of the saddle towers. So the first family, it's a 4-dimensional family of configuration. Therefore, gives a 5-dimensional family of minimal surface. And this is mixed boundary. The second family, it's new, and I'm very excited because this is this is again a 4-dimensional configuration, and it's non-degenerate, means that we can use the implicit function theorem to open it, and contains Schwarz edge surface, including the O edge surface that I discovered. It contains the rhombohedral gyroid. So means gyroid and Schwarz edge surface belong to the same 5-parameter manifold. So this is a new one, and these two, it's not very good because they are degenerate in the sense that we cannot apply the implicit function theorem. But I still numerically invested them, and this one contains the tetragonal gyroid. But I need some more investigation to see that this this can actually work, the construct can actually work. And the gluing catenoid, so what's the balance condition? Here is the formula for this talk, and that means that if I glue in this way, I glue 0 to P, and in the other one, I glue P to Q. Then I need this thing to be, this is Weierstrass beta function, P tau minus epsilon P tau plus C. And actually equals so anyway, this should be a constant. That is the balance condition. Then, and the C is defined here. I don't have time, so I won't go into detail. So what is this? This turns out to be the critical point. So if I say C equals 0, then this actually describes the critical point of the green function on the torus. And this has been investigated and published in 2010. So I'll give you a gentler, so I have electric charges, all positive in the space, and they are perfectly arranged. Now I want to put another charge in it. Where does it stop? This is the question. And I'm surprised that this is only solved in 2010. In 2010.
I did that.
Yeah. And so for us, any two critical points, not necessarily different, any two of them give us a minimal surface of genus 3. And so for general torus, there are trivial critical points here, here, and in the center. And so that's the 3 case. And for some, there are 2 more critical points here and here. And to give the general case, we should get rid of the C equals 0 thing. But the physics analog is to add a external field. Then where is the critical points? And we proved that there are at least 1 and at most 5 solutions. And I did some numerical work. So the colorful, so you just look at the left side. The colorful part is the part where we have 5 solutions. And the white part is the part where we have three solutions. And yeah, so also I would say I would go to there is a curve on the left. This is a very sparsely plotted curve because it's very numerically expensive. But there seems to be such a curve, which is a curve in the four-dimensional real space actually. But I projected it to the tau space, and this seems to be a curve that if you take a curve, go from here and here, then here we have 4 critical points, and here we have only 1. So numerically, I observe this. And then this curve goes to the boundary and intersect at something about 80 degrees. And this is a torus where there is a point. And there might be a curve. There seems to be a curve that I have 5 solutions here and 1 solution here. Okay, now this is frightening because I say 5, so any pair of solutions, not necessarily different, would give me a chip-paper minimal surface of genus 3. Then the existence of this point, which is not proved yet, means that on one side, I have 5 times 5, 25 possibilities. There might be symmetries that I can push it out, but that's a large number of minimal surfaces. And here, there's just 1. So, meaning the modular space of minimal surface near the catenoid limit is crazy.
So how many extra Jacobi fields are you getting at that point?
I don't know because this is, I only get it numerically. I don't know.
It's kind of like when you take the square and you move it up and down.
Yeah.
At some point you get a Jacobi field.
Yes.
And then the solution comes back down. You get a curve, but then you get unstable categories. Right? So when you did the picture,
yeah,
you're thinking of a stable one. But when you bring it close, there's also the unstable one, and they're in the same family, and they both make sure.
Yeah, I should compute the Jacobi field there, but first I need to get more precise to that point. Yeah. Yeah, the future, well, there are some promising projects like we can, that's very easy, completely classify all the boundary pieces. That seems easy. And I want to get all the orthorhombic and the monoclinic deformations of gyroid. I want to get all A3, so expand the O delta to a 3-parameter family, expand the H to a 3-parameter family, and find all, maybe I can find all examples with through symmetry. But these are challenging. Except, yes.
Bifurcations.
Yeah.
Bifurcations.
Yeah. Because mixed family has the orientation reversion symmetry, which I can push it out, then mixed family is a boundary.
Right. So I know you ever read my thesis, so I had sort of these 2 families, right? You have 2 kind of surface and the conjugate surface. They really come from that.
Yeah.
So you guys have 2, but then I showed that those 2 families are conjugate. The space, like going to cross layers are parallel.
Yeah.
So they cross at cross layers, CLP.
CLP, yeah.
They intersect along some CLP surface.
Okay. But the family can be described by antipodal pairs.
Right, but there's a surface and there's the conjugate surface.
Yeah.
For a certain CLP, I mean the CLP surface, it is
self-conjugate, yeah.
So the conjugate surface is congruent as a surface as a set.
So you're saying your family is not a manifold?
I actually don't know that, but you have the CLP surface where different things happen.
The RTD is
so
also
one family goes one way, another family goes another.
The RPD is also like this.
What?
The RPD, the Rhombohedral PMD is also like this. It's also self-conjugate. Yeah, and that's the end of my talk.
Questions?
So I guess I don't know if I made that conjecture. I might have made the pressure or just asked, is the space path connected? Is the space of all
the known examples are path connected.
Right. And one way to prove it might be to understand those limits that you said.
Yes.
And try to prove that you can always go to those limits.
Go to, yes.
And if you get close to those limits, then you can connect up.
That's the plan. Yes, that's the plan.
But I always wondered if that. And Matthias Weber always said, "Wow, I don't think so. You got the external surface. I'm going to connect that up." I don't know.
Yeah.
So now you know the hexagonal surface connects to the
Yeah.
driveway.
Yeah. And
The
I
driveway connects to the.
yeah, I actually believe they all, so the most crucial thing is the catenoid limit. They all deform to the catenoid limit. That's the.
Oh, okay.
Yeah.
Oh, okay. Got it.
Because the catenoid limit is the most complicated one. Hopeless.
That's what that picture is.
This one?
Okay.
Yeah, because you have 25 to 1.
Any other comments? Thank you.